All right. So just one point for points for assignment 1 and 2. So most of you should have gotten feedback already, I hope. And for the ones who didn't, I will meet the correctors just after the lecture now to discuss who's still missing and what needs to be done to get everyone's feedback. And then there was one more comment on assignment 4, where you have to, no, not that. Let's see. So in 4.6, you're asked to make a Python module or package, so that you know how to do. But you're also asked to make a setup script. And I'll either show this next week, or we will have a group session exercise on how to do that. But it's just another file that you need to add to make your package installable, essentially, which I think is very important, and it's good to cover. Yes, and then what else was asked? So the Python implementation, so that I will cover next week in the lecture. And you can only get points if you're in 43, 31 students. So if you're in 31 student, you can do the exercise, but you won't get points. But you can always you get bonus points in this assignment anyway. So you can do these exercises instead if you want to get some more points. Yeah, any questions regarding assignments? No? I hope they're fun. So once you've handed them in, there's going to be a peer review process, and then afterwards, I'm going to look through or maybe we have a voting system where we vote for the most beautiful picture, and you're not allowed to vote for your own picture. And then we look at the best ones, maybe the best ones and the worst ones. Or we look also at the person who comes up with the worst Python program. That's what I'm looking forward to. This is the first time we do this exercise, so I'm looking forward to what you come up with. Okay, so we stopped talking about this arange, and essentially it's the equivalent of the normal Python range. Oops, let's go. And just a warning here, sometimes you can get unexpected results when you use arange. So I give you an example. We have arange 8.2 and then 8.2.0.05. Right? So this is the endpoint. And then this is our step size. And not surprisingly, you get 8.2 and 8.25. That's the starting point and the endpoint here as the output. But now I do the following. The same thing, 8.2, but I do 8.2 plus 0.1. Right? So just twice what I had before, and I keep the step size. But the output is still 8.2 and 8.25. Right? So I would have expected to get 8.3 as the last item. Has anyone got a clue why this is behaving like this? Yeah? Right. So the reasoning is that on computers, floating point values you can't represent every floating point number exactly. So they're always rounded up to machine precision, and actually that depends on the underlying data types, how these are stored. And I come to that in a second again. But I can show this to you. It's very easy. So you just look at what the values are. So you do 8.2 plus 0.05, and you get 8.25. And then you do the same thing with 8.2 plus 0.1, and you get 8.2999999, which is smaller than 8.3, right? And so therefore, 8.3 is not included in that list here. So just for you to be aware of that. So if you want to be certain that the endpoint is included, right, you actually might want to add a tiny number here to make sure that the endpoint is included. So when you have a Python array, it has some attributes that you can always access. This is more a cheat sheet, but some of them are quite useful. So you can use a.data, for instance, to access the underlying data, the raw data, where the information is stored. But yeah, that's not often used. But this one is used. A.dtype is the data type. Remember, Numpy arrays always have the same types. Every item in the array has to have the same type. And here you can check which type your array has. You can check the dimension and the shape. So if you have matrices or higher order tensors, this will tell you how many dimensions or how many values you have in each dimension. A.size gives you the total number of elements in the array. So sometimes it's useful to specify exactly which data types you want to work with. And you do that by adding the dtype argument. So for instance, if you know that you're going to operate with integers, you can write np0s, length 3, and a dtype equals np.int. And so then you have float 32. So this is single position floating point values. Float 64 is double position floating point values. And then you have also complex numbers. And yeah, so I mean, for complex numbers, it's obvious. So there's a question on why. Sometimes it might actually be, why would you ever choose float 32 over float 64? Right? So float 64 gives you a higher position than 32. Yeah?
There are times when the position is not so important, but you have lots and lots and lots of data.
Yes.
Then having 32-bit float is nice.
Yeah, so this requires less storage per floating point value. And it typically also is faster when you do computations. So for instance, in graphics programming, so the GPU typically operates on 32 bits floating point values. While if you do scientific computing, right, when we are predicting the flow of blood of a patient, but we want to be damn sure that our simulations are correct. So we try to increase the precision. But if you do graphics, then you might want to get away with a smaller precision. And so here's an example how you can use these attributes. So if you want to create a copy of an existing Numpy array with the same shape, so the same vector length or matrix size or whatever, in the same data type, you can just write np0s, a.shape, and a.type. Then you get a copy, well, the same version of that array, but with zeros inside. So something to be aware of. So if you don't provide this data type, Numpy automatically infers the best suitable data type. So if you use np.array with just a list of integers, then you will get a Numpy array with integers. If you have a list with partially floats and partially integers, it will make an array of floating point values so that it can represent all these data types as floats. And then if you do something like this, if you try to do something pass in a list with floating point values, integers, and strings, then automatically Numpy will convert, so the Numpy array will be an array of strings. Right? It will, because it can't represent A as a number, so it will kind of choose the most general data structure where it can represent all these values. So just for you to be aware of that. Yeah, so
if you have one complex number, then it will be an array of complex numbers.
Yeah, it should be. Except if you have a string in there, then it will always go back to strings.
But if the others are numbers.
Right, I think so, yeah. So if you have one complex numbers and a bunch of floating point values, I think you should get a Numpy array of complex numbers. Yeah, that you've already seen. jump through it. So, of course, sometimes you want to go back to a Python list. So if you have an array and you want to go back to a Python list, you just use a.toList, and you get a Python list. So maybe this is useful if you, sometimes if you write a function, I'll show you an example down here. So let's say you have a function here, and it takes in something, and you're not entirely sure what it is. So it could be maybe a Python list, but it could also be a Numpy array. It could even be just a one integer or floating point value. But inside the function, you want to treat it just like it was in a Numpy array. And so there's this useful function np.sArray. It takes in something and converts it into a Numpy array. And it tries to do this without creating copies. And so then after that, you're certain that this a variable is a Numpy array, and you can operate on it. So the nice thing with this np.sArrays is that your function now works with all kinds of inputs. It works with lists, it works with Numpy arrays, it works with just a floating point value, and it even works for integers. So with that trick, it kind of becomes quite general, the implementation that you make. Yeah, one more. So let's say you have a Python function, and you want to create a Numpy array where where you want to evaluate that function at each point in your array. And so you have this np.form function. You pass in the function that you want to have evaluated, and then you provide the shape of the array. And so essentially here, this is now the function evaluated at 0, 0 for I and j, right? We have two coordinates. Here it's for 0, 1, and 0, 2, and so on and so forth. So then, of course, we can, at the moment, we just looked at vectors. Now we can generalize this to higher dimensions. So if you want to talk about matrices or tensors, this is how you do it. You just provide np.zeros, and instead of providing just one number, now we provide the length in each dimension. So here we have 3 dimensions, and in the first dimension we have 2 components, then we have 3 components in the second dimension and 3 components in the third dimension. And what you end up with is, if you plot this, you get 2 matrices of shape 3 times 3, right? These are these 2 components, and then 2, because we have 2 components in the first dimension. And then we can also, if we have 2 vectors, we can make a matrix containing these 2 vectors just by initializing np array, and then we pass a list with the 2 vectors. I think it's fairly straightforward. So if you want to go crazy, you can go all the way up to 32 dimensions. I've never, I mean, typically one doesn't really go that high. Just for you to be aware, if you want to have some fun. What is sometimes quite useful if you have an array and you want to convert it into, you want to change the dimension of the array. And so the way you need to mention it is, so a Numpy array is essentially just in memory, it's just a long list of numbers stored continuously. And there's this a.shape. So in addition, there's an attribute that every Numpy array has, and that stores its shape. And essentially, and this can be either just a single number, or it can be 2 numbers, or it can be 3 numbers, depending on what the shape is. And what this attribute does is it just changes how this long list of continuous numbers is being interpreted, right? I mean, you can see a long list of numbers either as a one-dimensional vector, or you could see that it's maybe the first n components are the first row of a vector, then the next n components are the second row of a vector, and so on and so forth. And so what you can do is, so I start with just a flat array, just a vector with 6 numbers, and then I change the shape attribute, and I say I want it to be a 2 times 3 matrix. Right? I want to reinterpret this array such as 2.3 matrix. And then if I print it, I indeed get a matrix with 2 rows and 3 components in each. And so what's important here is that we're still accessing the same underlying raw data. So if I now go ahead and change the 0, 0 component of that matrix, so which is this guy here, I set it to -10, and then I change the shape again, so I write a.shape equals a.size, comma, so I just make it again one long vector, and then I print it, right? So now I have the same vector as before, except that the first component now became a 10. So that's how you can play around with different dimensions and shapes as long as everything is consistent, right? So the total number of the length of the array always has to be the same. So I have 6 components, and then a matrix with 2 rows and 3 components in these is 2 times 3 elements, which is also 6. Yeah, there's also the reshape function that essentially does the same thing. I could have also typed in a.reshape 2, 3 instead of a.shape equals.
What's the difference between shape and reshape?
No, there's essentially the same thing. I think there's some technical differences that reshape, I think in certain cases it copies, but I'm not, yeah, you need to look up the manual if you want to know the details. So this is maybe something more traditional. You know, so if you go many years back, there was essentially C and Fortran. It's one of the 2 big low-level programming languages. And the way they stored higher-order tensors, like matrices, was different because they couldn't decide on what to use. So the C ordering, essentially, if you had a 2 times 3 matrix, in C, the way you store this in memory is that you first store the first row, and then you store the second row. Right? So in memory, you get this layout. In Fortran, you get first the first column, then the second column, then the third column. So you get such a layout here. And so, and in Numpy, we can actually choose which we want to use. Right? You can swap from a row layout to a column layout. And sometimes they're beneficial. Certain choices are better than others. But of course, if you have a one-dimensional array, it doesn't matter. Then you just have one row anyway.
You can also easily switch from one to the other by transposing the matrix.
Yeah, but then you get the transposed matrix. It's not the same matrix anymore.
Yeah.
So in Numpy, the default order is C. But you can change it by adding this order attribute. So if you explicitly want to have this column ordering, you can say order equals F. And then it will be stored in such a way. And so I mean, that's a bit technical, but the good thing is that Numpy is trying to be clever, and it automatically makes sure that, for instance, if you have a matrix in C ordering and a matrix in B ordering, and you try to add them up, right, then you have to be quite careful because they're laid out differently in memory. But Python is smart enough to convert, or Numpy is smart enough to convert the F ordering to C ordering. Actually, I'm not entirely sure in which way it converts, but it makes sure that things are consistent. So then the result will still be correct. So 1 plus 1 is 2, 2 plus 2 is 4, and so on and so forth. Yeah.
Will it still be commutative?
Sorry?
Will the ordering matter?
Right. You know, I'm not sure. So the question is, do you get the same ordering if you do A plus B or B plus A? And I'm not, well, we can test it out. So there's this, this line here tells you which ordering you're using. Right, so I can do, so if I do A plus B, I get C ordering. And if I do B plus A, I also get C ordering. Okay, so apparently you always get C ordering. And then this was the comment before. If you want to transpose the matrix, you can essentially, the way you do that is you just change from an F ordering to C ordering. So you don't have to copy any data values. You just change the ordering. Indexing, this we already know. Much of this is quite useful. We already know from Python lists, so we can slice if you only want to get the second to fourth element. We can do some fancy indexing if you only want to get the 0, the second, and the third argument item in our array. But here the important difference is that this slicing here only returns us a view into the data array. So we don't get a copy out, but we essentially get a view really on the existing data structures. And the reason why this is important is because once you do assignments on this, right, if you say a, if you use this line and then equals 5, you would actually change the original data array. You would set the 0, the second, and the third entry of the data array to 5. Right, so that's what I'm doing here. So I change my original data array by using these operations here. And so the last one, a.colon equals 0, right? You change your entire array to 0.
A with the column does not make a copy.
No, that's what I mean. So when you use this indexing and slicing, you get a view and you end up operating on your original array. There's no copy being created in these operations here. So the same thing generalizes to 2 dimensions. So if I have an array, a matrix of size 2 times 3, right, then my indexing, of course, also needs to have 2 components. The first one in the x component and then in the y component. And so, for instance, if you want to get the third column, you set, this is your column index. So you said you want all components. This is the row index. So you say you want to have everything, you want to have all the rows, but you want to fix everything to the third column, which you have here. Right? The same here. So if you want to get the second row, what you say, you fix the row value, and you want to say, I want to have all the columns. Then you get the second row. So this is quite useful. This is quite cool what you can do then. So imagine you have this large matrix here. With all kind of numbers, it doesn't really matter here, but it's a matrix of size 5 times 6. And now you want to extract a submatrix. Well, what you can do is, for instance, so let's say you want to get the submatrix consisting of row 2 and 3 and every second column of that original matrix. Right? Maybe you want to set some values, so extract something on that. So how do you do that? Use our fancy indexing. You say A, and then as the first component, we say 1 to 3. Right? That gives us the row second and 3. And then we also want to get every second column. And the way you do that is no endpoint, no starting point. And remember, the last item in this indexing was also always a step size. So I added 2 here to get every second row. And then this is our view that we get into our original array. And so now I could start operating on that. Same example now. This is again the point that the slicing operates on the original array. So if I create a matrix consisting of ones, then I extract a view into the second row, which I call B. And then I set the first component of that row to pi. And then I print the original matrix again. I now have my ones everywhere except that the first component of the third row has been set to pi. Right? So you really be aware of it that when you do the slicing, you need to be aware of the fact that you're operating always on the same array. But sometimes you actually maybe want to create a copy, and then you need to explicitly call the copy function. Right? So you can do slicing and then .copy, And then what you get with the output here is indeed a copy, and you can start changing it without changing the original array. Yeah, and so this is really different to the Python lists, where a colon makes a copy, always makes a copy. So then we have loops. So let's say you wanted to loop over a matrix, over each element in a matrix. Right? One way you could do that is you loop over the row indices, and the number of rows you get by a.shape, the first component. And then you loop over the column indices. You just have for loop, use the standard range, and the number of columns you get by the a.shape second component. And then you could do some assignments, right? You can say aij equals some function value. The problem with that is that it's really ugly. Well, from a Python perspective, it's really ugly. And it's not entirely clear that here we know that it's a matrix, but maybe sometimes it's a matrix, maybe sometimes it's a vector, maybe it's even a three tensor, right? And so if we don't know this in advance, it's not clear how many for loops we need to have here. So one little bit more Pythonic way of doing it is by replacing the indices by a for loop where we access the elements directly. So we can write for row in A, and then for each element in that row, we can call our function. So that's a lot more Pythonic because we can avoid all the indexing, but it still has the problem that we need to know how many dimensions we have in our tensor. So what do you do if you don't know the dimension? Well, one trick is that you could change the shape into a one-dimensional vector and then do the element-wise operation. Right? So I could have done a.shape equals what was it? The a.shape attribute to change it to a vector size and then change it back again. But there's again another function, a.revel, which is a bit more robust than accessing the a.shape directly. So essentially that returns a flattened version of our array, which I know is going to be 1D, and then I just have one loop. Yeah. So then sometimes it's useful to also know the indices of the array components. And the way you do that is with the nd enumerate function. So you can pass in a Numpy array of any dimension, and then you put this into a for loop, and then what you get is for each element you get its index and you get its value. Right? And the index now might be 2 components if you're a vector, but it might be 5 components if you're in a 5-dimensional tensor. Right, so now let's move on. So that was all about creating tensors, but now let's do some more interesting array operations. Let's say we want to have we have a vector and we want to multiply it by 3 and subtract 1. What you can do is you can just literally write this operation as if it was a floating point value. And the reason for that is because Numpy automatically employs so-called array operations. It performs these operations here on each element-wise in your array. Right? And so this A here, this might be a matrix, it might be a vector, it might be a higher dimensional tensor, it doesn't really matter. It just takes each element, multiplies it by 3 and subtracts 1. And then you get the result as a new array. And why would you want, so first of all, it's obviously it reads much more elegant, but it's also much, much faster than looping over each element manually. And I want you to demonstrate that. So here, we test now two implementations. One where I loop over the elements manually, and then the second one where we do this array operations. So how do we do that? I use this time module, import time, to clock how long certain parts of the program takes. Then I create a long array with 10 million entries, ranging from with values ranging from 0 to 1. And so then I start my timer. Time.clock just gives me the time right now. So I save this as a T0 variable. So then what I do is I create a new Numpy array of the same size. I loop over each element in my input Numpy array, and I perform this operation that we want to do. So 3 times a minus 1 for each element. Once I'm done, I stop the clock, and then I print out the result. So let's look at that. So I run it. Yeah, it's running. There we go, 7.995 seconds. Okay, so now, I should hide this. So now let's do the same thing again, but with our array operations. So I have a second timer here, and I now write b equals 3 times a minus 1. Right? It's the same thing as before, and I stop the timer again. Now I run it. So this uses our, oh, and there we go, 0.118. Okay, so we just saved, what was it, almost 10, well, not quite. We went from 8 seconds to 0.1 seconds. So it's a 20 times increase almost, 50 times. Okay, so it's really worth removing loops over elements when you operate on Numpy arrays. Right, so let's see what we actually got. 67, a speed up of 67. That wasn't so bad for a much shorter implementation. So these operations work automatically if you use multiplication and subtraction and addition, but they also work for more complicated mathematical operations. So Numpy has a bunch of functions implemented automatically, so you can use np and then the function name. So for instance, sinus, arcsinus, sinus hyperbolicus, log, exponential, square root, and so on and so forth. So Numpy comes with a lot of functions that you can automatically use on arrays.
Does it have inner and outer product?
You need to check. Yeah. So the question is, does it have inner and outer products? And if it's not in Numpy, I'm sure you find a library that sits on top of Numpy that does it. So there's this SciPy. Well, yeah. So just for you to be aware, there's also the standard math modules. So for math import sinus, for instance, if you try to use that, that will also work on Numpy arrays, but it's going to be slower than the pure Numpy implementations. So it's always preferable to use the Numpy implementations than the Python math ones. So then, of course, sometimes it's we have functions where we don't have a standard implementation in Numpy, our own functions, and these we also would like to have vectorized. So to give you an example, let's say I have my function here, and what it does is if the value, the element is larger than 0, it should return 0, and otherwise it's x squared. Right? Now, if I define this function and I just would try to apply it to a vector A, like this, it wouldn't work. Because what happens is that you pass in the array in here as the variable A, it shows up as the variable x here, and then here in the if statement you're trying to compare the array with a floating point value, right? So rather than automatically looping this into an element-wise loop, it will just pass in the array itself and use it as an argument, which is not what we want. So what you do then, of course, you could now add a loop again, maybe outside here or inside the function, where you loop over each element of A, but that defeats the purpose. And we know that's slow. So instead what we do is we use a helper function in Numpy. It's called np.vectorize. And what it does is it takes in the name of a function and it returns a vectorized version of that function. And now if I call my vectorized function with the input A, my array, then I get the expected result. So you can try this. There we go. So now the function has been called successfully, and for every, I had this print statement for every inside the function in here. And you can see that it prints out each element. Yeah, there's some cheat sheet for the mathematical operations that you have available. And it looks like actually that inner is not available, but it might be. Yeah, I'm sure it's in one of these sub-packages in here. Yeah, so this is a cheat sheet if you're looking for something specific, but of course if the documentation is even more extensive. Okay, I have 8 minutes for plotting. I might, if we don't make it, then I just continue next week. So I've already shown you a little bit of plotting at the very beginning. And maybe the most important thing that you need to take out of this is that there's really good documentation online. So I mean, I will show you the very basics, but as soon as you want to have something more advanced, just look to the documentation of Matplotlib. And something that for really advanced plots, what I like doing is I like going into this Matplotlib gallery. It's essentially a web page where you have loads and loads of examples of people who have done fancy plots. And you can click on the example, and then you get the code that was used to create that plot. Right? And that's a really good starting point for, you just go through the example, you find something that fits more or less your purpose, and then you use it as a starting point for your own code. But so if you just want to plot a simple function, let's say we have this function up here, and here's the Python implementation. The way we can plot that, we can't plot the function directly. We can only plot data points, x and y values. So what we need to do is we need to create some x values. I use np.linspace here from 0 to 10. And then I use this, I apply this function for, I evaluate this function for all the data points. So I get another array out here that contains the function values for all my x coordinates. And then what you can type in is plt.plot xy. And you get a nice plot of that function up here for these data points. And so of course, if I only had, let's say, 4 data points here, oops, you would see that the So now if I see now I only use 4 data points, and you can now see that the function approximation is very rough, right? And it does a linear interpolation between each data point. So if you then want to get a nicer representation, you just increase the number of data points here. So now it's nice and smooth. And so of course then the next thing that we want to do is we want to customize our plot a little bit. So the third argument is an indicator that specifies how the line looks like. So you can make it red. And there's an argument for making the line thicker, for instance. And then we also maybe want to change it such that here we want to maybe change the y-axis such that it starts at 0. So the way you do that is you use this pl.ylim, and you provide the limit. Okay, so then your plot looks like this. So then if you want to have multiple lines in your plot, you just repeat calling this pl.plot function for all the data points that you want to plot. So here I have xy and xz as data points, and then you get 2 lines. So here's a bit more advanced example. So now we have a label, a legend here, and we have text on the axis. So how do you, and we have different styles of the lines. So how do you do that? When you plot, you can add a label attribute that will, with the text that will show up here. Then you can have the color attribute more explicitly than before. Before I had just this :R, but I guess a nicer way of doing it is just writing color equals blue or color equals red, right? And then you have the line width that we've seen before, and the line style. So line style, if you just have a single minus, it becomes a thick line. If you have a double minus, it becomes a dashed line. So then you can add some X label and Y label. You can add a legend with a locator that just, the locator is an indicator where it should be on the left, right, bottom, left, right, and so on. And that's it. Then you call plt.show and you see the plot. One thing that's really useful is you can also save the plot as a PDF file. So pl.savefig will write out the plot as a file, and that's really useful if you write texts like your master thesis or your bachelor thesis. You can generate all your plots programmatically and insert them into your LaTeX document, for instance. And the nice thing is if you do it this way, right, it becomes reproducible. So if you change some parts of your code, you just run your entire system again, it generates all your output files, you compile your document again, and you have an updated version of your thesis. Yeah. There's loads of different types of plots, right? If you want to have scatter plot, I'll just show you an example here. So now instead of here I use pl.scatter instead of pl.plot, and then you get a plot like this. But again, if you look through the gallery, that's really the best way to start. Maybe just one last tip here. Actually, I haven't. So all the plots that you've seen were already prettier. So if I should have moved this. But by default, actually, the matplotlib plots look really ugly. And there's, of course, you could do loads of tweaking to make them look prettier. But a much faster way of doing that is by importing the seaborn library. So the seaborn library, it's for data analytics mod package. But it also updates the matplotlib standard style. And so if you quickly want to have a much nicer style, what you do is you just do from matplotlib, import your plotting stuff, and then afterwards you write import seaborn, and that updates your pyplotlet style. And so afterwards you get a much, much nicer plots than before. Okay, I managed to present plotting in 8 minutes. Are there any questions? No? Then next time we'll get integration of C and Python. See you next week.